All right, so today we have Alex Rolle from the Technical University of Munich, who will be telling us about the homology inference for the degree-Rips bifiltration.
Yeah, thanks for the introduction. So yeah, in the last few years, as I have started getting involved with research in TDA and computational topology, the AATRN series has been, yeah, really like a really useful resource for me. So I'm especially glad to be able to participate in it. Yeah, so the title is Homology Inference for the Degree-Rips Bifiltration. Today, I'm not going to present some big homology inference theorem about degree-Rips. My goal is sort of more modest than that, maybe. But I want to do a few things. So first of all, I'll describe degree-Rips, and in particular, give the definition. And then I want to talk about sort of one way to approach thinking about homology inference questions in this setting, and also importantly, why I think it's interesting to do that, and why for degree-Rips in particular, I think this homology inference sort of way of thinking is a particularly fruitful way of sort of understanding how this construction behaves. And then I'm gonna sort of throughout, I'll be talking about one particular example in quite some detail, which I think is sort of gives a bit of an impression of what's going on here. And also sort of, as I said before, why I think homology inference is a useful way of thinking about degree-Rips. And maybe the last thing I'll say before I get started is that, yes, like please interrupt me if you have questions, especially because I was not sure as I was putting together this talk exactly how much detail to go into, especially with definitions and things like that. So if I'm talking about something that I haven't introduced, please, and you'd like to know more about how it works or the definition, please let me know. Okay, so yeah, let's start. So the degree-Rips complexes, this forms a two-parameter filtration, which is based on the Vietoris-Rips filtration, which I won't define because it's sort of familiar to people in this seminar. So I'll define the degree-Rips complexes on this slide, but first let me make a couple points about it and sort of where we're headed with this. So the first point is that the degree-Rips complexes of a sample reflects the underlying probability measure. So if, like the Vietoris-Rips filtration, the degree-Rips complexes are going to take a finite metric space as input. And if we think of this finite metric space as being a sample from some unknown probability measure on the ambient space, then what I'm claiming is that the degree-Rips complexes we compute of this sample reflect something about the underlying probability measure. And I'll make that precise later on in the talk. But I want to say right away that this is in contrast to the Vietoris-Rips filtration. So because of the Hausdorff stability of the Vietoris-Rips filtration, we know that if we consider the case where the size of the sample goes to infinity, then the Vietoris-Rips filtration we compute from these finite samples will converge in some sense to the Vietoris-Rips complexes of the support of the underlying probability measure. So the Vietoris-Rips filtration tells us about the support of the probability measure, but not about different probability measures on the same support. And in particular, degree-Rips is more robust to outliers than Vietoris-Rips. And this is a big part of the original motivation, as I understand it, for studying this object. And I'll give an example that sort of gives an idea what I mean as we go along. Okay, so now I'll define it. So degree-rips takes two parameters, as I said. The first parameter S is a distance scale. This is the distance scale we'll use for the Vietoris-Rips filtration. And the second parameter K is a natural number, and this is a density threshold. And so the definition, which is due to Lesnick and Wright, looks like this. So we take X to be a finite metric space, and we consider all of these subsets of X that depend on our choice of parameters. So if we fix some distance scale S, then we take the subset consisting of all those points, little x, such that the ball of radius S about little x contains at least k sample points, at least k points of x. And then as S and K vary, this forms a two-parameter filtration of X. And then we get degree-Rips filtration just by taking the Vietoris-Rips complexes of this thing. So at parameter S and K, we take this subset XSK, we reuse S for Vietoris-Rips, and now we get a, maybe I'll just note that if another way to think about this is we can start by taking the Vietoris-Rips complex of X with respect to the distance scale S. And then at parameter SK, we're looking at those points. We're looking at the full subcomplex of the Vietoris-Rips complex on those points that have degree at least k minus 1, I guess, in the one skeleton of the Vietoris-Rips complex. And so this characterization in terms of the degree is where the name degree-Rips comes from. Okay. And so before we get to an example, let me just mention if I take a point X in my space and I think of S as being fixed, then as I vary K, what's happening is that as I increase K, I'm filtering out points that do not have enough neighbors in their ball of radius S. And so I hope it's at least sort of intuitive why this kind of construction might be somehow robust outliers. If we take a point that is an outlier with respect to the distance scale S, it doesn't have very many neighbors. Then as we increase K, this point will get filtered out. We won't use it as a vertex in our Vietoris-Rips construction, and it won't affect, in particular, the homology. I think a fairly intuitive idea.
Alex,
so
let me interrupt really quick.
Filtration, Alex, and so if we take, yep.
Can you hear me?
Sure.
Yeah. So the audio is okay, but not great. So I'm going to ask myself and Facundo and Sunyuk, we'll turn off our videos so you won't be able to see us. Hopefully the audio will improve just a little bit. If not, I'll let you know, in which case I'll have you turn off your video as well. But keep going with your video on and we'll let you know.
Okay. All right. Yeah, thank you. So as I was saying, we have this degree-Rips. This degree-Rips construction is a two-parameter construction. So if we take homology, we get a parameter persistence module. And so here on this slide, along with showing you an example of what happens with a particular point cloud, I also want to just explain how I'm going to summarize the homology of degree-Rips in this talk. So here on the left, I have a point cloud. This is a noisy sample from an annulus. most of the points are concentrated on this annulus, but there are also some outliers in the center. And then on the right, I'm plotting what's called the Hilbert function of the persistence module we get by taking homology. So let me explain what that means. It's quite straightforward. So this square is the degree-Rips parameter space. We have the distance scale S on the horizontal axis and the degree parameter K on the vertical axis. And so for any S and K, I get a degree-Rips complex, and I take its homology, so I get a vector space. And then this Hilbert function is just counting the rank of those vector spaces. And so where the color is white, this means we have 0-dimensional homology. And where the color is light, this light shade of gray, we have rank 1 homology. And where the color is a darker gray, we have higher rank homology. And so in particular, this light gray region that you see here, this is the region where, at least just looking at the ranks of the homology vector spaces, we're getting the homology of the annulus. I think what you would hope to see is that there's some reasonable range of parameter space where the homology we're seeing looks like the homology of an annulus. And maybe I'll note further, if we let K be 0 or maybe 1, so that this degree requirement is vacuous, so we look at this vertical slice along the bottom, then we're just getting the Vietoris-Rips filtration of this point cloud and taking its homology. And so here, then this function that's plotted here is just at each value of S, it's just counting how many bars we have at that value. And so what you see, which is, I think, maybe what you would expect, is that if we just look at the Vietoris-Rips filtration of this kind of point cloud, we see a lot of spurious features in H1. But as long as we let K be a little bit larger, those spurious features are filtered out, and we get this region where the homology is rank 1. And for those who are interested, I mean, if you're interested in multi-parameter persistent homology, you can look at other invariants. You can look at, so here it says this computation was done by Rivet, which is this software for 2-parameter persistent homology. So you can also look at things like the graded Betti numbers, and you can sort of see what this 2-parameter persistence module looks like. But for our purposes in this talk, just looking at the Hilbert function is already going to tell us sort of everything we need to know about the persistence modules we encounter. All right, so if you have questions about how I'm displaying this 2-parameter persistence, please ask. But for now, I'll move on. So this is sort of a further example. Here now I'm showing the output of degree-Rips on three point clouds. So at the top, I take this point cloud that's concentrated on an annulus, and I look at its Hilbert function. This middle row, this is what we just saw. We have, again, the same point cloud concentrated on an annulus, but we've added some outliers sampled uniformly from the disk inside the annulus. And this output has changed, as we see. And then for sort of comparison, as a third point cloud, I just have a uniform sample from the whole disk, and I look at its at H1 of the degree-Rips of that. And so, I mean, what we can see is that degree-Rips can distinguish these 3 point clouds. And so what I want to, first of all, sort of draw your attention to here is that this, to some extent, gives sort of evidence for what I said, that degree-Rips is robust to outliers. So here, when we started with this point cloud concentrated on an annulus, we get this large region of parameter space where we get the homology of the annulus. And then if we then add outliers, this sort of strong topological signal that we had that was indicating this one-dimensional feature in H1, this has not been destroyed, but it has been changed in a substantial way. And so the question now that I'm interested in is what can we say, how can we be precise about the effect that outliers have on degree rips? What is the mechanism that sort of controls how this output changes to this output? So this example comes from a recent paper of Blumberg and Lesnick. And so let me start by explaining the results that they obtained for degree rips and how they bear on this this example. So in order to state their result, I first want to define the Prokhorov distance. So the Prokhorov distance is a distance between measures in eta on some common metric space Z. And this is the definition. So this formula isn't too important for the talk, but I think it's useful to look at it at least a little bit. So the way the Prokhorov distance works is we consider all closed sets A, and then we look for each A, we look for the infimum of the delta for which we get these two inequalities. So what is this saying? It's saying that if I take some closed set A and I measure it with mu, then I need to be able to bound this above by applying eta to A, but I have to be able to be flexible in two ways. So first of all, maybe this doesn't quite bound mu A, but only up to this additive factor of delta. And also I need to measure with eta, not A itself, but some slightly larger set, the delta thickening. So all those points that are within delta of A. But if I enlarge A by delta, and then I'm willing to also add delta, I get an upper bound on the measure that I got with mu. And then this inequality is the same, but with mu and eta reversed. So this is the Prokhorov distance between measures. This is a standard way to measure the distance between measures on a common metric space. And I'll note that there is a Gromov-Prokhorov distance, which is analogous to the Gromov-Hausdorff distance. So this gives us a way to compare two measures on two different metric spaces. And as with the Gromov-Hausdorff distance, we consider all pairs of isometric embeddings into some common metric space. And then now we use those isometric embeddings, we push forward the measures that we had, and then we compare the measures, these push forward measures using the Prokhorov distance. But the definition isn't so important for what I'm going to say, but it gives us a way to compare measures on different metric spaces. So let's look at an example. If X is a finite metric space with n points, big N points, we let mu X be the measure on X that we get just by counting the number of points in some set and then normalizing by the total number of points. So this is sometimes called the uniform measure on X. And now if Y is obtained from X by adding in some additional point Z, which I'm thinking of here as outliers, and here the number of points in Z is little n, then the Gromov-Prokhorov distance, this is easy to check, between mu X and mu Y is bounded above by the number of outliers divided by the number of points I had originally. So Blumberg and Lesnick say that this is a sense in which this Gromov-Prokhorov distance is robust to outliers. So what this means is if I start with any set X and then I add a small number of outliers, it doesn't matter where I put them or what relationship they have with the geometry of what I started with, then this Gromov-Prokhorov distance will be small if this number of outliers I add is small. And so then the idea of Blumberg and Lesnick is to prove a stability result for degree Rips, where now we compare point clouds using the Gromov-Prokhorov distance instead of, say, the Gromov-Hausdorff distance. And this is a very nice idea, and I think it's very natural from the point of view of the stability theorems that we're familiar with in TDA. And because of facts like this about the Gromov-Prokhorov distance, this is going to say something about the robustness of degree Rips to outliers. And so here's the result that they prove. If X and Y are non-empty finite metric spaces, then for any delta greater than this Gromov-Prokhorov distance between these associated measures, the degree Rips complexes of X and of Y are homotopy interleaved with respect to this affine map. So I should make a couple comments here. If you're not familiar with homotopy interleavings, you can take homology, which is what I've been doing anyway with degree Rips. So if you take the homology of degree Rips and degree of X and of Y, you get these two parameter persistence modules. And then now this homotopy interleaving distance, this homotopy interleaving gives us a regular interleaving between these two parameter persistence modules. So if the Gromov-Prokhorov distance between X and Y is small, then this delta is small, and we get a interleaving between the homology of degree Rips of X and of Y that has a small additive term, but it also has this multiplicative term 3 in the spatial parameter, and that doesn't change. And Blumberg and Lesnick also show that this factor 3 is tight, so it cannot be improved. So within their framework, which, as I said, I think is a very natural framework for this setting, this is the best possible result. And so this is.
Can I ask a question?
Yeah, sure.
You said the factor 3 cannot be improved. What would improvement mean?
So improved would mean proving this result where now you get a factor of 2 here, or a number smaller than 3. And so I want to be careful about, I don't want to say, because I don't remember the details of their counterexample. But what they show, I suppose, is that you can find families of finite metric spaces such that I guess get arbitrarily close, such that then the degree Rips complexes of these are not homotopy interleaved with respect to any affine map where the factor here is less than 3.
I see. I'm sorry that I'm going to ask another question. I'm not sure if this is something that you're familiar or not with. So do they work with Gromov-Prokhorov with the parameter lambda equals to 1, or with a generic lambda? So let me tell you why I'm asking that question. So because if you work with a lambda, you will obtain possibly some lambda showing up in this affine etc. map. And I would expect that as lambda goes to 0, the coefficient 3 becomes 1.
So where does this lambda show up in the definition of the Prokhorov distance, or the Gromov-Prokhorov distance?
So it would appear, it would show up multiplying delta. When you have plus delta,
here.
Exactly. And when lambda is 0,
also
Not there, only in the
Only here.
additive. Yeah.
Okay.
And when lambda becomes 0, you have no additive freedom. Let me say that.
Right. Right.
And then you can prove that Prokhorov with lambda equals to 0 is equal to Wasserstein with p infinity.
Hmm.
And then when you just continue with the constructions, you will get that Gromov-Prokhorov with lambda equals to 0 is the same as Gromov-Wasserstein with p infinity.
Hmm.
And then I would suspect that the stability for lambda equals to 0 is very similar to Gromov's also stability. And therefore, I kind of wouldn't expect a 3 as a slope there. I would hope the slope becomes 1. It's just a conjecture, but I became very curious while you were describing this, and maybe we can talk about it later.
Right. So I will not try to answer your question directly because I don't remember the answer. But I'll say a little. This might be interesting. Roughly speaking, the way the proof goes is that you start by considering. So when you define degree Rips of X, you start by taking this two-parameter filtration of X, which they call the multi-cover bifiltration. So this was this thing. No, you know what? Actually, in fact, I'm going to stop myself there because I don't want to say anything wrong, and I haven't looked at this proof in a while. But thank you for the question, and maybe we can talk about this at the end of it.
Sure. Yeah. Thanks.
Okay. So this is the robustness result of Blumberg and Lesnick, which is, as you can see, is quite general, and has this form that we sort of are familiar with from other stability results. But something very nice that they do in their paper is that they evaluate it on this example that I was talking about before. And so let's look at that now. So this figure, these plots now come from their paper. And so they consider these same 2-point clouds, or I mean, not these same 2-point clouds, but 2-point clouds drawn from the same probability measures. So again, a uniform sample on this annulus, and then a uniform sample on the annulus with outliers added inside the disk. And they plot the persistence modules you get using Rivet. So these are the plots produced by Rivet, and so this gray shading is has the same meaning as in the plots I showed you before. But now there's some additional information that comes from Rivet, like these green and orange dots. And what they do is they show that if you use their stability result, in fact, not exactly the version I showed you, but another version that they have for the special case where one point cloud is a subset of the other. So you use their stability result and you assume that you know what happens on this point cloud without outliers. And then you can see by looking at the output of Rivet that this gray region where the homology is rank 1 corresponds to some indecomposable summand. So in particular, these internal structure maps in this gray region all have rank 1. And then using that and using their stability results, they find that there's a non-empty region, which is this region shaded black here, in the parameter space for this point cloud, where the homology has to be non-zero. So just using the fact that based on the number of outliers that have been added, you get some bound on the Gromov-Prokhorov distance between these 2 point clouds. And then this gives you, then you get this interleaving, and this tells you that this black region here must have non-zero homology. And they say that this is sort of, this is, this gives us, we can sort of see that this stability result that they have doesn't explain very well the observed region where we have non-zero homology for this point cloud. And so in particular, what this result sort of doesn't tell us is if we increased the size of the sample, how should we expect the degree rips in this noisy case to change? Is the region where we have non-zero homology, is it going to continue, is it going to shrink and sort of converge to this small region, or is it going to stay the same or do something different? And we don't know. And so this is the kind of question that I want to answer in this talk. Okay. So to do that, let's talk about a more general way to define degree rips. So I'll say that a metric probability space is a metric space X together with a Borel probability measure. So a probability measure on the Borel sigma algebra. And now I'm going to define degree rips in this context. So as before, I have a parameter S, which is a distance scale. And I have a second parameter K, which is a density threshold. But now K lives is continuous and it lives between 0 and 1. So now to get started, so let X comma mu be a metric probability space. And I'll say that the uniform filtration is a 2-parameter filtration of X, where at parameter S and K, we take those points such that the measure of the ball of radius S around X is greater than or equal to K. So this is, this looks like what we saw before, except now instead of counting neighbors in this ball, we measure it. We measure this ball using mu. And then just as before, we get the degree rips complexes by reusing this parameter and taking the Vietoris-Rips complexes of this metric space. Okay, so this is something straightforward that you can do. And I'll mention this uniform filtration. I mean, this is some extremely natural construction, I think, and this has appeared in a number of works on multi-parameter persistent homology. So it appears in the paper of Blumberg Lesnick. They call it the measure bifiltration. And it's also sometimes called the multi-cover bifiltration. And I'm calling it the uniform filtration for reasons that maybe I'll mention at the end of the talk. But okay, so this is a definition. And first, as an example, let's see how it relates to what we saw before. So if X is a finite metric space, and we let mu be the measure on X that we saw, so mu X of A is just the size of A divided by the number of points. This is the uniform measure on X. Then if we take degree rips of this metric probability space, where we use this probability measure, this recovers the degree rips bifiltration that we defined at the beginning of the talk up to a rescaling, just up to rescaling the parameter K by the number of points in X. So this is a generalization. And sort of, I guess, maybe a reason to consider this generalization is because you can then prove a theorem like this. So this theorem, let's say, so this says that if mu is a probability measure on Euclidean space with compact support C, and we let Xn be an IID sample from mu of size n, then as n goes to infinity, we have this convergence in probability of the degree rips complexes of Xn to the degree-Rips complexes of the underlying metric probability space, C comma mu, with respect to this homotopy interleaving distance. So the homotopy interleaving distance is the distance you get using homotopy interleavings that we saw before. And so again, you could, if you want a result just in terms of ordinary interleavings, you can take homology of these degree-Rips bifiltrations, and then now this dhi becomes just di, the interleaving distance between the persistence modules. So yeah, let me make a couple comments about this. So first of all, I'm attributing it to me and Luis Skokla because this is written down in his thesis. Actually, this statement is not written down there, but there is a stability result for degree-Rips, which is quite different from the Blumberg-Lesnick result talked about before. And then this result is sort of a simple corollary of that stability result. And so this, let me say, this is one way to make precise what I said at the beginning of the talk, that the degree-Rips complexes of a finite metric space reflect the underlying probability measure. In the sense that as the sample goes to infinity, we converge to something that we compute from this underlying metric probability space. And here the notation is quite telling in that here this degree-Rips depends on both C, the support of the measure, and mu, the measure itself. And somehow it's the fact that these degree-Rips complexes of the underlying metric probability space reflect both the support and the measure that makes these questions about robustness to outliers quite subtle. And so I'm going to talk about an example next that'll maybe make that a little bit clearer. Okay, so with this in mind, we can now go back to this example and approach it in a different way. The example of these point clouds we saw earlier. So I'm going to define a weighted annulus, ARQW, to be this specific metric probability space. So I take the annulus with inner radius R and outer radius Q. And then I also take the inner disk, the points with norm less than R. And so as a metric space, I just have a disk of radius Q, but I put a uniform measure, a different uniform measure on each piece. And so what you should imagine is that on the annulus, I have a uniform measure with a high value of the density, and on the inner disk, I have a uniform measure with low value of the density. And this measure of the inner disk is controlled by this third parameter W. So you should imagine that W is some small but non-zero number that gives the weight of the inner disk. And if we want, we can then view the point cloud here that we saw before as being a random sample from this metric probability space, as long as we choose R, Q, and W appropriately. And then now, in the case that W is 0, I will have a similar definition, except now I take the underlying metric space to be just the annulus. And this is very important. So if the weight of the inner disk is 0, then I don't just change the measure, but I also change the support. And the underlying metric space is just an annulus. Okay. And so now the main theorem that I want to talk about today is a calculation of the degree-Rips complexes of these metric probability spaces up to homotopy type. So let ARQW be a weighted annulus with W greater than 0. Then there are continuous maps, phi L, for L going from 0 to infinity, such that for any S and any K, we have this formula. And so what this says is that these continuous maps, they give curves in the degree-Rips parameter space, and these curves are the boundaries of regions where the degree-Rips complexes have this specified homotopy type. So if K is larger than phi 0, the complexes are empty. Phi 0 is in red here. Phi 1 is in blue. And so if K is between phi 1 and phi 0, then the degree-Rips complexes have the homotopy type of S1, and so on. This yellow curve is phi 2. So in this little yellow region, we get the homotopy type of S3. And then if K is less than phi infinity, which is in black, then the complexes are contractible. So these odd spheres, people will recognize from the Adamaszek-Adams computation of the Vietoris-Rips complexes of the circle, and that's where they come from. So I'll say more about that maybe in a minute. And let me just mention the theorem says that these continuous maps exist. And then in the paper I wrote about this computation, there are explicit formulas for these curves. They're quite complicated, but there are formulas. So there's even like a little Python script I wrote that when you put in R, Q, and W, it will plot these curves. And so this is in a way the main interest, at least for me, of this computation is that you can see exactly what the region is where you get S1, for example. So now I didn't say on the previous slide, but there's a version of this result when W is 0. And this is the picture you get for that case. Now it looks a little bit different. These boundary curves aren't continuous anymore, but the meaning of the colors is the same. Again, this blue region is where the complexes have the homotopy type of S1, and this yellow region is where you get S3, and so on. So now let me compare this result to the result we saw on finite samples before. Because, I mean, sort of looking at this picture is sort of the main reason that I did this calculation. So in the top row, we have the same picture we saw before. We have this finite sample. And here we just as before, we use Rivet to compute the Hilbert function of H1. And we see the region where we get rank 1 homology. And then on top of this, I've plotted the boundary of the region where the underlying metric probability space, where its degree complexes have the homotopy type of S1. So the way I think about this, these black curves, they give the boundary of the expected region where we should see rank 1 homology. And then the same down here. Again, this black curve gives us the boundary of the region where the underlying metric probability space, where its degree Rips complexes have the homotopy type of S1. And so this, I claim this answers the question that I posed earlier, which is what should we expect to happen if we took bigger samples? And this signal that we see here that gives us some signal that there is some feature in H1, what will happen as we take a bigger sample and in particular add more outliers. And this tells us that what we should expect is that it will eventually converge to be gray inside this region. And so one of the things we notice right away is that here, even with this small, relatively small sample size, the observed region is already quite close to this expected region. So I'm gonna finish up my talk now. And just by mentioning a few sort of avenues for future work. So let me first say that the calculation of these that I've just showed you has two parts. So the first part is to compute the uniform filtration of these metric probability spaces. And what you find is that for every choice of S and K, what you get is an annulus, or it's empty, or it's a disk. And so then by computing the inner radius of every annulus that shows up in this uniform filtration, we can now apply the Adamaszek-Adams calculation of the Vietoris-Rips complexes of the circle, because the Vietoris-Rips complexes of an annulus have the same homotopy type as the Vietoris-Rips complexes of the inner circle of that annulus. So one of the reasons that I did this computation is, partly because it sort of directly responds to these experiments in the Blumberg-Lesnick paper, but also this is a setting where we sort of have all the tools we need to get this very precise result, because we have this computation of the Vietoris-Rips complexes of the circle. Hello?
Sorry, I think somebody was accidentally unmuted, but I just muted them.
Okay, yeah, thank you. Yeah, maybe that is the sign that I should wrap up. So let me just say that thinking about further work, I think there are many interesting sort of future sort of calculations you could think about doing from here. But the main point I want to make now is that some of these intermediate steps or partial calculations are already extremely interesting. So the uniform filtration is, I'd say here it's related to the bias variance trade-off for density estimation. So one of the things you might ask is sort of how the way of measuring density that we're employing here is related to the classical topic in statistics of density estimation. And there's a very close relationship. And so in particular, if you imagine that your underlying probability measure comes from a density function, then the homological features that you see in this uniform filtration are related to the homological features in the superlevel set filtration of that density function. And if you know how these homological features in the superlevel set filtration of the density, how they survive in the uniform filtration, sort of for what region of parameters they survive in the uniform filtration, this tells you something about the amount of bias you can accept in like a classical non-parametric density estimate. So this is, I think, a very interesting topic, and you can sort of investigate this without being able to compute Vietoris-Rips at all. And then going a little bit further, if we take degree rips, but we restrict ourselves to the components, the connected components of degree rips, this is related to a number of popular methods for clustering. And so understanding questions about inference or robustness here are related to, I think, questions of very practical interest having to do with these clustering rhythms. So I think there's a lot of room for sort of interesting further calculations, even if it's not possible to do the sort of complete calculation that we were able to do in this particular setting. And that's all I wanted to say today. So thanks a lot for your attention.
So just we unmute ourselves and thank Alex for the wonderful talk. Are there any questions or comments?
I'll ask a question. So thanks, Alex, for the nice talk. And the audio was fine. I think turning off our videos did help. I I've seen some talks on this related subdivision Rips complex, which I think is related to the degree Rips complex. Is it correct to say that the subdivision Rips complex can be quite expensive to compute, but in contrast, the degree Rips complex is not so inefficient to compute? Because you're sort of, for the degree Rips, you're just taking subcomplexes of the actual Rips.
Yeah. So thanks for the question. I mean, this is an important aspect of all this that that it definitely makes sense to discuss in a talk like this. So there is this thing called the subdivision Rips bifiltration, and I won't give the definition for people in the audience, but in a way you've already seen it, because there's this uniform filtration that I defined. The subdivision Rips bifiltration gives something that is equivalent to the uniform filtration. So there's a pointwise homotopy equivalence between this subdivision Rips bifiltration and this uniform bifiltration. So the homotopy types of everything you get are the same. And the uniform filtration, or equivalently the subdivision Rips bifiltration, is really well behaved theoretically. In particular, it has a really nice stability result, again using the Prokhorov distance and interleavings, but now using just ordinary additive interleavings, and this is immediate. But both of these things, the subdivision Rips bifiltration and the uniform filtration, are very expensive to compute. There is interesting work on computing the uniform filtration, and if the ambient dimension is very small, this is feasible. So I don't know if there's publicly available software at the moment, but there have been papers about this, and so this is maybe tractable in some settings. But yeah, it's definitely not as computable as degree Rips. So part of I think the motivation that at least a lot of people have for considering degree Rips is that this feels like something that should be computable in sort of practical, even for sort of larger data sizes. And this is a topic of further work. So currently, like Rivet can compute degree Rips. I mean, this, as I said, these are the plots that I've showed. It's the sample sizes I showed in this talk are starting to get to the limit of what Rivet can handle at the moment. But yeah, I think there's current work on this of improving our ability to compute degree Rips.
Thanks, appreciate it.
I have I cannot call it a question. It's more like speculation, and so I mean, of course, I don't understand the details about how you prove the result, but suppose that we would want to prove a similar result more in general, and say for a sphere of dimension n, when n is possibly larger than 1. We don't yet know the full, we don't have full understanding of the persistent homology of spheres, but in the homotopy types and all that. But suppose that we only make some synthetic assumptions, like there exists a set of critical values, and then say the homotopy type is fixed between two critical values, etc.
I can't hear you.
Oh, sorry. So
I don't know if it's just my side or.
Can you hear me now?
Now I can hear you.
Yeah. So I was saying, suppose that we make some synthetic assumptions about the way the homotopy type behaves between two critical values. I was wondering how far could you push your arguments to conclude that certain functions phi sub L exist, etc., etc. I mean,
right. So I mean, this is a very good question, and in a way, I think it's such a natural question I should have thought more about this than I have, and I haven't really. I suspect that one could. My feeling at the moment is that one could carry this out. I don't. I don't know how much more complicated this sort of the geometry, the like Euclidean geometry you need to do. I'm not enough of an expert or just practiced enough in sort of elementary Euclidean geometry to maybe anticipate some of the issues that could come up, but it feels to me like you should be able to extend this computation and again say something like that you find that the spaces you get in the uniform filtration are these thickened spheres, and again you try to compute their inner radii, and then or you use partial calculations of the homotopy types or persistent homology of Vietoris-Rips on these higher dimensional spheres, you should be able to get some extension or like partial calculation along the lines of what just showed. And maybe let me just quickly say one thing about why this would be, I think, especially interesting to do is because one of the if you could compare the result of what happens in the plane with what happens in 3 space, for example, this would tell you something about how the convergence of degree rips is affected by ambient dimension. So I said that on this finite sample, you can sort of see that even with just 500 points, and so only something like 25 outliers in the center, the observed region where you get H1 is quite close to the expected region. And what I would expect to happen if you were looking at a 2-sphere in R3 is that if you looked at the same sample size and computed H2, the observed region where you get H2 is going to be much bigger than the expected region because the convergence to the limit is slower in the ambient dimension, but actually seeing how much slower would be very interesting.
I see. It just occurred to me that if you accepted working in, say, R3 with the L infinity metric, not L2 metric, but L infinity, then annuli, the behavior of Vietoris-Rips there is somehow easier in the sense that thickenings of the unit sphere in R3 with L infinity metric, right? It would be a box. The homotopy types are much simpler in that case. You have only 2. And at the same time, the notion of annuli in that case is simply the thickening, which is known to be homotopy equivalent to Vietoris-Rips. So maybe an analysis in that case would be easier because first there are fewer homotopy types, only 2, and then the annuli coincide with exactly the object that calls shots, if you know what I mean, like you said there.
Right. Yeah, that's a very interesting idea. Yeah, that's a good point. And I would also, I would imagine the computations maybe would also be easier in the finite sample case too, if you took the L infinity metric on the sample points. Yeah, that's an interesting suggestion.
Anyway, I want to give the floor to anyone else who may have other comments or questions in the meantime. All right, if not, then I have one more question. So I was wondering if you might have carried out some calculations for the case of clustering. And I was imagining, suppose you have 2 disks with very high density in the plane, and then the background density is lower. It's still uniform, but say some alpha. I'm very curious to see what the curves might become in that case, and what the different regions may indicate.
Right. Yeah. So this is, I mean, this is a. So I've thought a little bit about this. And let me first of all make a point about something. One thing that's different in the case of clustering is that one thing that was very simple here is that we only had one feature we were interested in, and the question is just, is it alive or not? But in the clustering case, what you imagine is you have some probability measure that somehow has multiple clusters, and then you're looking for the regions where you're looking to see how these, what happens to these features as the scale increases. And so if you just look at the uniform filtration, what you expect to happen is, let me see. So in the uniform filtration, if you just look at vertical slices of the uniform filtration, so what happens when you fix a particular spatial parameter value, what you get is, because like in the example you mentioned, the measure you're talking about is defined by a density. And then what you get as you let this spatial parameter grow is the super level set filtration of something that's like sort of a smoothed version of this density, which is what you get by the value at a point, instead of being the value of the original density, is the integral of the density on the ball of, centered at that point. And so I think you can compute what happens in the uniform filtration for this. You can compute these smoothed density functions and then compute the uniform filtration. And this is a setting, I think, where it would make sense to prove like a more general inference theorem. But maybe to finally answer your question, like, no, I haven't actually written it all down and computed what what curves you get, even though I think that is a feasible thing to do. But yeah, it's definitely an interesting thing to do for sure. But one thing, maybe I'll say one last point about this, because it's an interesting question. I think a really interesting example for something like this is, imagine a setting where you have some number of clusters, and they're different, not just in the prominence, like in the sense of how long the bars are in the super level set filtration of the density, but also in how fast they decay. So you have one mode of your density function, which is sort of very gradual, and another mode that's very sharp. Then, even though the prominence, as we like normally measure with persistence homology, is the same, the one that has the fatter mode is going to survive for longer in the uniform filtration and also degree rips. And quantifying this and like looking at particular examples, this is something, yeah, I definitely like to do.
Thank you for the answer. Well, are there any more comments or? All right, if not, let's thank Alex again. Thanks very much, Alex. I will stop recording now. If people want to